Look, what this boils down to is that you have a fairly decent understanding about what the graph of y equals log base b of x looks like. This is called transformations of logarithmic functions. So if we confine ourselves to y equals log base b of x, where b is greater than 1, which according to the program of studies, which is the Bible, sorry, I marked you absent, I'll change that, okay, which is the Bible that I have to follow in terms of what I teach, we are not expecting you to do transformations of logarithmic functions for bases between 0 and 1, although those functions exist. And you should know what they look like, just not about the transformations. You should know that this function of log base b of x, where b is greater than 1, looks something like that. And we'll get to in a little bit how you could graph it on your calculator. The bottom line is, and we run into problems here because I've used b for the base, the problem now becomes, can you graph things like that? Or, I mean, I don't really believe that you would ever be asked to graph that, but you would be asked things like, what's the domain, what's the range, what are the intercepts of the function? So if you factor the 4 out of the 4x minus 12, you can see very clearly that we have a parameter a of 2, a parameter b of 4, and this is where the confusion might come in. That parameter that I'm calling b, which is 4, is not the base, which is 3. Okay. We have a parameter h of 3 and a parameter k of 8, so you should be able to take this graph that you're looking at and transform it to answer questions about domain, range, intercepts, and all of that. The other part of this, well, let's stop there. So that's what the first part of this assignment dealt with, transformations. Keep in mind, finding the transformations of this graph, that task is no different than finding the transformations of the graph of y equals x squared, or of y equals sine of x, or of any function that you're familiar with. So take a look at your work here, please. Does anybody have any questions on page 389 that you would like me to go over? Go ahead. 10A, certainly. Oh yeah, and the other thing that we did talk about, by the way, was applications, but we're going to continue to see them over and over again. So 10A says only a vertical translation has been applied to a particular graph, and the new graph passes through a certain point. We have actually done questions like this, but it would have been in the past, and you can go back and look, that it wouldn't have been this. It might have been, we're going to apply a vertical translation to that graph, and it's got to pass through this point. And how we did that, and I'll get back to the original question in a second, is we said that the new function must be the old function plus k, because we're told the old function undergoes a vertical translation. So I'm using the made-up function, not the one that's actually in the question. And then what I taught you, maybe even in 20-1, if you had me for 20-1, is we refer to what's going on here as a missing parameter. So the idea here is that you would put in an ordered pair, and it would be 9, negative 4. So you would put negative 4 here, you would put 9 here, you would solve for k and get k equals negative 85. So we would have to translate y equals x squared 85 units down to make it pass through that point. And it's negative 85 because 9 squared is 81, and we have to subtract it. Okay, well, let's give our heads a shake and come back to reality here, because there was no x squared, it was this function. So the new function, and I'm using the word new here because I didn't use function notation. I didn't say f of x turns into g of x. Will be log base 3 of x plus some parameter. And you know, the way I've written this, I could very easily see somebody mistakenly thinking that that's what I mean, but that is not what I mean. This is typically how something like this would be written. If I were king, and I'm not, I would force everybody to write it this way, so it's very clear that that k is not with the x, okay? Either way, mathematically, it's the same thing. Now, we're going to do the same thing I did earlier with the made-up function. This is x and this is y. We know the graph passes through 9, negative 4. And I suspect you could probably finish it now. But I'm going to go through and do this. I'm going to go with the top one, simply because that's how it's usually written. So we put in the y coordinate of negative 4, and then we put in the x coordinate of 9, plus our parameter k. I mentioned this yesterday. I'll mention it again. Nobody in the room should have to use your change of base formula to know that log base 3 of 9 is 2. If you do, things are just going to fall to pieces very, very quickly for you in the remainder of this unit. Log base 3 of 9 is the exponent. So log base 3 of 9 equals the exponent to which you raise 3 to get 9. That's what log base 3 of 9 is. So you have to raise 3 to the 2 to get 9. And now what we can do is we can subtract 2 from both sides and see that k is equal to negative 6. If, on the other hand, we had a horizontal translation to y equals log base 2 of x, so we're going from y equals log base 2 of x. We're transforming that into y equals log base 2 of x minus h, because it's a horizontal translation. And it's passing through, this time, 8, 1. Oh, thank you. I should have read it more carefully. It is not a horizontal translation. I'm going to do this one anyway, just for kicks in a minute. Thank you, though, Reagan. It says a horizontal stretch, which means we're transforming it into y equals log base 2 of bx. And here's a huge fault of mine. Every time I teach this course, I say, and I've been doing this for close to 30 years, quit being so lazy. We really should have a set of brackets around that. Okay, we really should. And that's going to come up again today in the lesson. So is it that it passes through 8, negative 1? I can just take a quick look. 8, 1. So this graph passes through the point that when x is 8, y is 1. So we put those numbers in for y and x. We put 1 in for y. And then we have log base 2 of, whoops. We put 1 in for y, and then we have log base 2 of b times 8, which I would probably write 8b. So you're trying to solve that. Let me rewrite it that way. This is log base 2 of 8b. So now you're trying to solve this, and we're going to spend a lot of time tomorrow and the day after solving equations. But for something simple like this, you go back to that tip I gave you, which is if you don't understand it, translate it to the other form. So 1 equals log base 2 of 8b means 2 raised to the 1 gives you that 8b. So that's 2 equals 8b, which means b is 1/4. Now, we want to be careful here. Are you okay with that? Because if the question said, what is the stretch factor, then the answer is 4. And I don't know what it says. It says, determine the equation of the transformed image or function. So we don't need to reciprocate that. We say since b is 4, since b is a quarter, it's y equals log base 2 of 1/4 x. Is that okay? All right. As I said, just because I started this, I'll finish this, which isn't in the actual question. If it were a horizontal translation, we would have the following when we substitute in the ordered pair. What we're going to do is no different in principle to what we did here. We wrote this in exponential form. So if this were the question, and I know it's not, we would write 2 to the 1 equals 8 minus h. So I'm going to move the h to the left side where it becomes positive and subtract the 2. H would be 6. This function would be y equals log base 2 of x minus 6. Is that okay? Okay. Ian?
In 10a, the equation that we figured was negative 4 equals log 3 to the 9 plus k. And when you solve for log 3...
Can you just stop for a second? Are you talking about this question here?
Yes.
Okay.
When you solve on the left-hand side, your work, it shows negative 4 equals log 3 to the 9. And then you go negative 4 equals 2 plus k. Because you made log 3 the
Log base 3 of 9
of 9.
is equal to 2.
Right. How come you didn't say 3 to the negative 4 equals 9?
Because there's a k here.
How come on 10b you were allowed to do 2 to the 1 equals 8? Because you used the number from the...
Because there's just a logarithm equals a number. There's nothing else after the logarithm. No. Other questions? Okay. So you're given, it's called the Ehrenberg Relation, and it relates the height in centimeters of children between the ages of 5 and 13 to their masses in kilograms. Obviously, this would be an average equation. It wouldn't be something that would be working for every student. So predict the height of a 10-year-old child with a mass of 60 kilograms. So our equation is log of m equals 0.008h plus 0.4. And it says we're trying to find the height when the mass is 60. So we have to put 60 in for m. And I'm going to have log of 60 equals 0.008h plus 0.4. So, you know, what I would say to you here, Marcel, is this is just a number. I mean, the value of it may be of importance, but it's just a number. So solving this equation is no different than solving 3 equals 2x minus 11. So what you're going to have to do is take log of 60 and subtract 0.4 and then divide by 0.008. And that will give you the answer. Okay. All right, let's move on. The remainder of the questions were 8 and then 12 to 16 on page 27 or 28 of your textbook. I'm looking, I'm guessing it's 28. This is just a lot of extra practice in working with logarithms. So any questions there? Okay, then go ahead. Sure. I was just going to say, though, based on what I observed when I said any questions, it was like you were flipping through these questions for the first time. And I'm not here to give you crap. But I am here to tell you that if you want to do good at a course like this that's quite academically challenging, you know, you have to try these questions. And if you don't try them, you get out of this course what you put into it, which might be a pretty low mark on this unit exam. I've mentioned this before. This unit is difficult, so make sure that you try these questions on your own. Anyway, William, did you say 16? Okay. Let's take a look at 16. Ah, yes, 16 is a classic question. You would see this on a diploma exam with almost 100% certainty. It's a very difficult question for you to do, and what I'm going to do, William, is I'm going to leave this one until about 5 minutes into the first lesson, because if I show you how to do it now, it's going to be very, very confusing, but if I show you how to do it in about 5 minutes, it's going to be very, very easy. Okay? And I would rather take the easy route than confusion, always. Any other questions, though, other than that one?
14.
Sorry?
14.
14? Okay.
14C. C.
This is a multiple choice question.
That's the answer I got.
Oh, you got C.
Yeah.
Okay. So, we're asked to find the value of t. I'm going to rewrite both of those equations in exponential form. The first equation, log base 2 of x equals 3, means 2 to the 3 equals x. So just, even in doing that, we've revealed to ourselves what x is equal to. It's equal to 8. Not 9, 8. Because it's 2 raised to the 3, which is 2 times 2 times 2. So x is equal to 8. When we rewrite the next equation, log base 2 of t equals x in exponential form, we end up with 2 raised to the x equals t, and we're asked to find t, so we need to take 2 raised to the x, which is 8, and that will give us t. And I believe that's 64, isn't it? Can you tell me what you did so that I know as a teacher?
I was putting 3. So I just, you know how 2 to the power 3 is 8?
Yeah.
Apparently I wasn't realizing, but every time I was doing it, I was thinking it's 3 times 3 times. I wasn't paying attention. I was thinking 3 times 3 times 3.
Oh, okay.
27, then multiply it.
Those powers of 3 and powers of 2 can be very confusing. So be very careful. Even though the numbers are small, you know, and another common mistake here, Jonathan and everybody, would be to say 9. That's why I said 2 to the 3 is 8, not 9. And I suspect that many people would get 9. They would just think 9. They would see the 3 and the 2, and you would get choice B. Anyway, the answer is A. Shazmida? Sure. Do you agree that when you rearrange this equation for x, you reveal to yourself that x is 8? Okay. And do you see that the second equation gives us this? When you rewrite log base 2 of t equals x, you write 2 to the x equals t. So t is equal to 2 to the x. Right? That's what this is saying. But x is 8. So all I'm doing is I'm putting this in here. 2 to the 8? Oh, is it not 64? Oh, my mistake. What was I doing? I must have done 2 to the 6. Yeah, that's what I did. I did 2 to the 6 times another 4 is 256. Is that right? Okay. Does it say the answer is C? And you said you got C. So you got the right answer. I don't know what you did, but you did get the right answer. I was the one who screwed up. So thank you, Shazmida. 2 to the 8. Another fault of doing something just in your head is 256, is it? Okay, so the answer is 256. All right, we're going to have to get started here on the next lesson, which deals with laws of logarithms. And I don't really believe from memory that this is a lesson that takes a long time, but it is a lesson that foundationally is very, very important to everything else we do in this unit. It's going to lead to how you would be able to answer the second part of that written response question which you were given yesterday. So we're going to be looking today at applying the laws of logarithms to, I'm going to summarize all of this here, to solve mathematical problems. Whether they're algebraic or numerical doesn't matter. So whether we're dealing with laws of logarithms being applied to logs of numbers or to logs of variables, it won't matter. So what are the laws of logarithms? Well, we've got laws for exponents, right? When you multiply a common base, you add the exponents. When you have a power of a power, you multiply the exponents. You have all of these laws for exponents, which means there must be laws for logarithms, because logarithms are just exponents written in a different way. And we're not here to prove these laws. We're here to be able to use them. Some of you might be able to dig down deep in your brain and understand why these laws work, but we don't need to. So there's a product law, a quotient law, and a power law for logarithms. So first of all, what does the product law say? This is very important that you listen to what I'm saying verbally. The product law says the logarithm of a product is the same as the sum of the logarithms. So if I'm taking the logarithm of a product of two things, instead of multiplying those two things together and then taking the logarithm of the product, what I can do is take the logarithm of each of them and add those two logarithms together. Now, this is not intended to be a definitive proof, but what I'm telling you apparently is that log base 5 of 20 times 11 should be equal to log base 5 of 20 plus log base 5 of 11. And I'm not sure why I have brackets around the 11 and not the 20. That's not important. So how would we go ahead and find log base 5 of 20 times 11? Well, if you have a TI-84 calculator, you can use the log base function. I have to use the change of base formula. So I have to enter log of 20 times 11 divided by log of 5. That's how I would calculate log base 5 of 20 times 11. And I get this number. If I wanted to find out what log base 5 of 20 plus log base 5 of 11 is, on this calculator, I have to use the change of base formula. I would go log of 20, I'm working on the right-hand side here, close brackets divided by log of 5, close brackets, plus log of 11, close brackets, divided by log of 5. And I get the exact same number. Okay, and again, this isn't a proof, but I hope you trust me that I didn't choose numbers that it happens to work for and all the other numbers it won't work for. So the bottom line is they are equal. Before we go on to the quotient law, I want everybody to ponder this question. When you're multiplying two things, and you don't have to answer out loud, when you're multiplying two things, does the order of multiplication matter? When you're adding two things, does the order of addition matter? No. No to both of those. So where the m and the n are in this doesn't matter. Now think of this question. When you divide two quantities, does the order matter? And the answer is obviously yes. 100 divided by 5 is 20. 5 divided by 100 is not 20. And the order in which you subtract things matters. 11 minus 2 is 9, but 2 minus 11 is not 9. So The quotient law says the logarithm of a quotient is equal to the difference of the logarithms, but listen very carefully. The argument will contain a numerator and a denominator. It's the numerator that becomes the argument of the positive logarithm, and it's the denominator that becomes the argument of the negative logarithm. So you take the logarithm of the numerator minus the logarithm of the denominator. Just to show that to you, if I said, is this true? I'm not going to spend time entering into the calculator. I've already done that. You're going to end up with 2.386294752, regardless of how you do it. Okay. The final one is a fundamental law, which is really important. And those of you taking calculus, you need to not confuse this, because we're going to be doing this in calculus very shortly, working with logarithms. You need to not confuse this with the power law for derivatives. This has nothing to do with differentiation. Those of you not in calculus don't know what I'm referring to, and that's fine. What the power law says, and I want you to notice that I really should have brackets around the m to the n, and I see that in your note package I didn't put the brackets. You should have them there. That's that thing that I should get better at not being lazy about. This says that the logarithm of a power is equal to the exponent times the logarithm of a base, which is a very cool formula. It leads to all kinds of simplification rules that we end up being able to perform. So what does this mean? It means that if I tell you, determine log base 8 of 7 to the 3, if you want, you could take 7 to the 3 and take the base 8 logarithm of it. Or you could just take 3 times log base 8 of 7. And, I know that I like the TI-83 calculator, but to show this to you on a TI-84 calculator, using the log base function, so log base 8 of 7 to the 3, that's log base 8 of 7 to the 3. It's that number. Instead, I can just go 3 times the log, 3 times log base 8 of 7, and I get the same number. Okay. So let's take a look at these. Write each expression in terms of individual logarithms of x, y, and z. I'm going to be asking you throughout these questions, how many of you see the answer already? Okay, I'm not going to do that with the first example, but I'm going to be doing that a lot. Since this is, and I'm going to also be doing an awful lot of writing that I don't need to. Since this is log base 3 of x squared times y, that means it's log base 3 of x squared plus log base 3 of y. This is the product law. The logarithm of a product is equal to the sum of the logarithms. By the way, those 3 logs that you're looking at the top of your page are on your formula sheet. Those 3 log laws are on your formula sheet. But log base 3 of x squared is the same as 2 times log base 3 of x. And I want to point out a couple of things here. This isn't just me being a picky person. How you write this is important. There are 3 lines of text. And I have to run a program to get something started. Give me a second. There are 3 lines of text associated with logarithmic expressions. There's only two being used in this. Okay? There is a line that is the subscripts, which is showing bases of logarithms. There is a line which is neither subscript nor superscript. It's showing the main items in the entry. And there may also be a third line. For example, here, log x and y are all written on the same line. The bases are written as subscripts, but there is also a superscript. And it's important for you not to just be lazy and just write down, like if you just wrote everything in a basket and threw it down on the paper. That needs to be organized. It's going to be helpful for later. My question to you is, and I'm going to get rid of all of the highlighting here. How many of you see that this is equal to that, and you could even have just done that to begin with? You're going to separate out the products, the factors that give you the product, and any exponents are going to lay out in front because of the power law. That being said, how many of you see that the answer here is going to be log base 6 of x minus 3 log base 6 of z? And that's probably most people, I would think. You want to be very careful, because if this were a written response question, I really believe that this should probably be written. And there's this bracket thing again. It's not, let me explain something. When I say I'm being lazy by not putting brackets around the z cubed, that's all it is. It's not wrong to leave the brackets out. But as a teacher, I think stressing that it's in brackets reinforces the idea that that exponent can go down in front. Okay. Any questions with A or B? All right. So this, how many of you feel as though you could write out the final answer right now? Okay. Just make a mental note of what you believe it to be, and then I'm going to break this down. I'm going to show far more steps here than we ever need to do, even on a written response. This is log base 2 of xy cubed minus log base 2 of z squared. Because of the quotient law, it's the logarithm. I better check something here. Good. I thought maybe I put a plus here, but it is a minus. The quotient law says you subtract the logarithms, the logarithm of the numerator minus the logarithm of the denominator. But this argument of xy cubed is a product, so I can write this as log base 2 of x plus log base 2 of y cubed. And then I have minus log base 2 of z squared. And now I can lay all of those exponents out in front and have log base 2 of x plus 3 log base 2 of y minus 2 log base 2 of z. When I first started this question, I said, how many of you believe, and I know you were a little more hesitant here because there was 3 variables, but I asked you how many of you believe you would know what the answer would be, and I asked you to make a mental note of it. Is that matching what you suspected? Okay. So, and I really believe, unless it's a written response, I really believe that I expect everybody to be able to just do that. How many of you believe you know how to write the answer here? I would like you to write it down if you think you know, and then we'll see if you're right. And I will give you a hint here. There's a catch to this question. In various places throughout this course, there's that one thing that many students forget to do. Maybe half the province on the diploma exam forget to do. This, I would hope that we have talked about this so many times that none of you are going to say h is 15 there. You're going to factor that 3 out to write it as y equals f of 3 bracket x minus 5, and then say h is 5. That's that one. I don't know if you remember, but there were 3 or 4 questions on the first exam, and some of you got nailed 3 or 4 times on that. You lost a lot of marks. This means, and I'm going to give you the detailed solution first, and then I'm going to explain the shortcut. Log base b of x to the 4 minus log base b of y to the 10 z cubed. And since this is a product, we have y equals log base b of x to the 4, and then we have minus, since it's a product, we're going to take log base b of y to the 10 plus log base b of z cubed. And my question now is, how many of you essentially have for an answer 4 log base b of x minus 10 log base b of y plus 3 log base b of z? What's the mistake there? It's already done. I've already screwed up by writing that. Marcel? I need brackets. I'm subtracting. I'm going to get rid of this unit 1 stuff. I'm subtracting this entire logarithm, and that entire logarithm is a sum of 2 other logarithms. So I have to subtract both of these. How many of you, by the way, did do that? Okay, that's good. And really, this is that grade 7 or 8 thing that it's so frustrating for a senior math student to make the mistake of doing, because you understand logarithms, but you make a very elementary error. This becomes 4 log base b of x, and this will be minus this first logarithm, which is 10 log base b of y, plus, minus, because we're subtracting log base b of z times that 3, which goes in front. And here's the shortcut. And this is just, I don't know, it's something I think I was either told in high school or it occurred to me. Any part of the argument that's on the bottom will have a negative in front of the logarithm. Like there's a z cubed on the bottom of the original argument of the logarithm. So that is going to become 3 log of z, but it will be negative because that part of the argument's on the bottom. So anything on the top is a positive logarithm, anything on the bottom is negative. So for example, the first thing we have to do here is remember that a cube root is an exponent of a third, a square root is an exponent of a half. So we could use the quotient law, or we could use what I just told you. You're going to have a log base 7 of x to the third, which is going to become 1/3 log base 7 of x. You're going to have a log base 7 of y to the half, which is going to become 1/2 times log base 7 of y. But the x to the third is on the top, the y to the half is on the bottom, so that's the answer written out as a sum or differences of logarithms. Does that make sense? All right. It usually does. Use the laws of logarithms to simplify. So we're not using a calculator here with the logarithm function. What we're doing is saying log base 2 of 40 minus log base 2 of 5 is log base 2 of 40 over 5. Now I can't stop you from using your calculator to figure out what 40 over 5 is. And if you have to, that's fine. But I don't want us to use the log function or the change of base formula. 40 over 5 is 8, so this is log base 2 of 8, which is 3. And I've actually seen a little 1-mark written response question as part of a 5-mark question, which says, explain why log base 2 of 40 minus log base 2 of 5 equals 8. Or equals 3. And you would have to explain it. You would have to explain all of these steps. When we pack this together as a single logarithm, the 45 and the 15 will go on the top. The 25 will go on the bottom. I don't care how you figure out what 45 times 15 over 25 is. It's 3 over 5, 9, it's 27. I'm just figuring out what it is by canceling common factors. You can use your calculator. This is log base 3 of 27, which is another 3 because log base 3 of 27 is saying, what do you raise 3 to get 27? Log base 8 of 48 plus log base 8 of 4 minus bracket log base 8 of 15 minus log base 5 of 5. Wow. Does yours say log base 5 of 5?
No,
It says 8. Okay. Whew. That's an 8. So I'm going to write something down here. And ask how many of you see why that is correct. If you don't use that shortcut that I told you about, negative logarithms have arguments that are on the bottom, positive have ones that are on the top. You can make this very confusing, but when I get rid of these brackets, this is log base 8 of 48 plus log base 8 of 4 minus log base 8 of 15 plus, because I'm subtracting both of those, plus log base 8 of 5. You can see now why the 5 goes on the top. What I would always ask you to avoid is putting fractions within fractions. So we could have put 45 times 4 over and then had another bracket that said 15 over 5. Ian?
Isn't that also just, if you do put it under the complex fractions, you're just simplifying the
Sure. But why work with a complex fraction when you don't need to? Would be my response. There's nothing wrong with doing it that way. Okay. We simplify this and you end up with what I believe is log base 8, but I'm going to need some help here on the product and quotient. 64, I'm seeing people nod. And that is equal to 2 because log base 8 of 64 is the exponent to which you raise 8 to get 64. D, well, these are all positive logarithms, so I can write log base 21 of 7 times 9 times 1/3. That happens to be 21. So log base 21 of 21 is 1. We're still okay with this? 5 log base 10, these are base 10 logarithms, because it doesn't say. 2 log 5 plus 2 log 20, this is log of 5 squared plus log of 20 squared. So before I can pack the separate logarithms into a single logarithm, I need to get rid of coefficients. I don't have to. There's other things you could do. Okay, but this is what I would prefer. Now I can write this as log of 25 times 400, because 5 squared is 25. 20 squared is 400. This is a base 10 logarithm, so I'm introducing that. This is log base 10 of I want to say 10,000. Am I right? Okay. So that's asking you to find the exponent to which you raise 10 to get 10,000. Well, that's 4 because there's 4 zeros on the 10,000. So this is 4. Could you have instead factored a 2 out from the original expression and had log 5 plus log 20, which would mean 2 times log of 5 times 20, which means 2 times log of 100. Well, log of 100 is the exponent to which you raise 2 or 10 to get 100. That's 2 times 2 is 4. It's like I've told you before, the math doesn't lie. As long as you're doing the math right, you're not breaking any rules, it will work. Let's take a look at the next one. How many of you see that the answer to F is 0? There's so many ways to see it. One of the ways is to move this 3 out in front and have 3 log x minus 3 log x. Well, that's 0. One of the ways is to leave the first term alone and write log of x cubed minus log of x cubed. Well, a quantity minus an identical quantity is 0. I have seen people do this, and there's nothing wrong with it. This is log of x cubed over x cubed, isn't it? Because it's a difference of logarithms. But x cubed over x cubed is 1. And that's saying, to what do you raise 10 to get 1? 0. Just have one more example left, right? So this is what I mean by saying this is not a long lesson. It's just a lot of drill and practice. Number 3 is putting things back together. It's not tearing it apart like where we started with example 1. It's packing it together with variables. And this will be log of, classic example of an incorrect answer. And I know some of you are going to pick this as a multiple choice. This is what it is. The z goes on the top because it's part of a positive logarithm. I mean, if I had this, then both the y and the z would go in the denominator. But I don't. So be very careful about that. Let me clean this up. This is log Okay. When I take a look at B, all of the logarithms in B have a coefficient of 1, which means you're allowed to, at this point, just pack it all together as a single logarithm. Log base 2 of x, well, x is going on the top because it's positive logarithm. The 2x goes on the top. On the bottom, we have an x squared, and we have a y. So any questions with that? We can, yep.
If there's the log base 2 of x squared, if that said 2 log 2 of x, sorry, 2 log base 2 of x, would we have to factor out, and then we can do that?
It wouldn't factor out. You'd take that 2 and you'd put it up top. So if this was a 7 here, you would write that 7 up top, and then this would be x to the 7. You need to get all those coefficients up top to make it work. Okay, let's clean up that argument. Okay, so this is log base 2 of 2 over y, because x times x is x squared on the top, and over x squared reduces to 1. So now we're going to start to wade into the territory that we had to go through with trig, which is that you can do a bunch of work with identities in trig and come up with an expression that might appear different than another expression that's the same. Hang on to your thought, please. So my question to you is, does anybody see why this is 1 minus log base 2 of y? Because it is. And it's likely to be that that would be the answer on an exam. The reason it's 1 minus log base 2 of y is now that I've gotten rid of the x's, I can put this back as separate logarithms. And log base 2 of 2 is 1. So log base 2 of 2 over y is log base 2 of 2 minus log base 2 of y because of the quotient law. But log base 2 of 2 is the exponent to which you raise 2 to get 2, which is 1. A couple of other things before we just finish off this lesson. And this is coming on the heels of what Ian was talking about with me a second ago. And you may never encounter this, but then again, you may encounter this. I can move that negative 1 in front of that logarithm up and apply it as an exponent on the y, and write this as the sum of two logarithms. And that would mean I could write that it simplifies to 1 plus log base 2 of 1 over y, because y to the negative 1 is 1 over y. And I'm going to show you something now that many of you will just realize I'm just talking in circles. Since this is a sum, I could write this as a single logarithm where I multiply these two arguments. 2 times y to the negative 1. Well, I hope you see that 2 times y to the negative 1 is 2 over y. It's the same thing that I have up here. There's so many ways that you can massage your answers here and just get them to appear differently by putting on a different mask. Anyway, any questions with that example? Ian?
How come for the example B, the last log 2 of y, log base 2 of y, how come that y is not on the numerator?
Are you talking about here?
No.
Above or below?
Above.
What's your question again? How come that y is what?
More above.
More above.
On the top one.
Here?
Yes.
Why is this y on the bottom? Is that what you're asking?
Yes.
Because the logarithm associated with it is negative. That's the rule.
So you don't write it as the first two are plus or added together.
Yeah.
Multiplied together, and then there's the second one subtract, so it's on the denominator.
Yeah.
The next one is also subtract, so how come it's not on the denominator?
Because it's not this. I think I know what you're asking.
What would it look like if it was that?
Then you would change this to minus. It would look like what we did here. You would switch the sign. As long as your logarithms, everybody, and this is what, I mean, you have to avoid this confusion because you don't want to analyze this every time. What you want to do is come up with a rule anywhere in math, a rule that's as broad as possible that you can say this is always going to work. And the rule here is as long as all of the logarithms are separate from each other. There's no brackets. There's no plus a whole bunch of logarithms in brackets. As long as the logarithms are all separate from one another, a positive logarithm will have an argument that goes in the numerator, and a negative logarithm will have an argument that goes in the denominator. Okay, we got a couple more quick ones to do. We're kind of winding things down here. This is log of x cubed root y. I would just like you to contemplate that. The intermediate step would be to say that this is log of x to the 3 plus the log of y to the half, and then say it's a product, so it's two logs being added, so I'm going to write the log of the product, and then finally to just say, well, half is an exponent that means square root. Here, I'm trying to mess with you a little bit, but again, talking about what Ian and I have been discussing, there's 3 separate logarithms here. So I can write it as a single logarithm, and any argument that's in a positive logarithm will form part of the numerator of the argument, and that's our answer. That's it. There's nothing you can do here. You can't cancel anything. Finally, I'm going to end this by saying that there's a huge, huge mistake that can be made with this kind of stuff. And I'll do this one first. If you have something like that, it's to say, oh, that's equal to log of a minus b. No, that's not a rule. Log of a minus b is not the log of a difference. Log of a minus b is the difference of logs. When you have that difference or sum, you have to have separate logs. And when you have the quotient or product, it's a single log. So be very, very careful about that. The reason I mentioned that is I know some people over here might say, well, can't I write this as log of a times b? Or maybe log of a times log of b. The answer is no, you can't do anything with that. Nothing. So on page 31 of your handout, 1 to 6 and 10 through 17, it's important that you get lots of practice with this stuff. You still have about 20 minutes here in class to get going on this. Give me a few minutes and I'll come around and give you a hand.